So in this chapter now, chapter 34, we want to talk about electromagnetic induction. Electromagnetic induction refers to the fact that when you have magnetic fields that are changing in time, then you get an induced current in a circuit. Typically, we'll be talking about coils as being the circuit, which is the simplest circuit that you can imagine. It's just a wire connected in a loop. And circuit means that you have to have a closed path for the electrons to move. So if you have a magnetic field changing in time, then electromagnetic induction tells you that that is going to be able to generate a current. So remember that in the 1820s, when this physics professor was doing a lecture in his class and he set up a current flowing through a wire, he had a compass. By chance, he had left a compass near this wire with current, and he noticed that the compass got aligned, that the compass moved, that having a current flowing through a wire affected or created a magnetic field, just like a magnet has one. So after that discovery that was published, then people immediately thought, well, if a current can produce a magnetic field, can a magnetic field produce a current? Right? That's a very obvious thing to wonder. If one thing produces this other thing, maybe this other thing is also, you can use it to produce the first one, right? So people started to play with magnets and currents and so on, trying to figure out a way to, using a magnetic field, say a magnet, produce a current. And it didn't take too long to people to find a way to do it. The first person to do that was Joseph Henry, an American scientist. He found a way to do that. He didn't publish, but almost at the same time, Michael Faraday was also working in this problem, and he examined the problem from all possible angles and discovered all of the properties that it had, and he was the one who ended up publishing. So what Faraday did was something similar to what I'm going to show you. So he used a magnet, of course, and a coil, just like I have over here. So people try many different ways, just putting a magnet in there and seeing what would happen. Inside a coil, nothing happens. A magnetic field, in this case, is not generating an electric current, right? But what was soon realized was that it didn't take that much to actually get a current flowing if you move the magnet, right? If you move the magnet in, there is a current, and the needle is moving in a particular direction, telling you that the current is flowing in one direction in the coil. But if you already have the magnet in and you pull it out, then the current goes in the opposite direction. So notice that if I go in, the needle goes one way. If I go out, it goes in the opposite direction, right? So if you want to have a continuous current flowing in this device, what you can do is you're going to have to keep shaking this in and out to produce a current, which in this case is going to be a current positive, negative, and so on, right? So as you can see, mechanical work, which is what I'm doing by shaking the magnet, can produce electrical energy, a current flowing in the circuit. Okay? Now you might wonder, okay, so you have a coil and you move the magnet and you can get a current flowing. What about you leave the magnet stationary and you move the coil? As you can see there, same thing happens. If I move the coil towards the magnet, it goes in one direction. If I move the coil in the opposite direction, it goes in the other direction. Right? So either I move the magnet or I move the coil, the result seems to be the same. There is a current that is induced in this coil. This is the coil that we're talking about, right? This closed circuit. So the first motion, or the first effect that I want to discuss, which is easier to understand with the stuff that you already know, is the motion of the coil towards the magnet. So let's start by thinking of an easier situation, which is you have a magnetic field in space. Let's say that it goes into the page. That's your B. And let's say that you just put a piece of metal, a bar made of iron, for example. And you take this bar and you give it some velocity. You pull it with a constant velocity. Suppose that that's what you're doing here. If you think about the charges inside that bar, well, you know that those charges, that the bar is full of charges. It is full of negative charges, electrons, which can move easily, right? As soon as there is a little force acting on an electron, the electron is going to move. It's a very light particle. So definitely, They will move if there is a force. What is the force that is acting on those electrons? Is the magnetic field putting a force on the electrons inside that bar? The answer is yes, right? If you have an electron, I'm going to draw a little electron here. Since the electron is inside that bar and the bar is moving, the electron has a velocity, the same as the velocity of the bar, right? If you have a charge moving in a region where there is a magnetic field, what happens to the charge? It would experience a force, right? To determine the direction of the force, you can use your right-hand rule. In this case, your velocity goes with the thumb as usual, right? The magnetic field goes into the page, and your palm is pointing towards the upper part of the screen, right? But it is a negative charge. Since it is a negative charge, the force, you have to flip it. So the force on that electron is actually going down. This is a magnetic force. We call that force Lorentz force. And that would push the electrons inside the bar. It would push them down, right? So after a little bit of time, after this bar has been moving in this magnetic field, what's going to happen is that the electrons are going to accumulate at the bottom, and positive charge, because the bar is neutral, are going to accumulate on the top. So now you have the top positive, the bottom negative. As soon as you have some difference in charge, positive on the top, negative at the bottom, there will be an electric field inside the conductor, right? An electric field that goes from positive charge towards negative charge. So let me draw that electric field there. The electric field goes from the positive charges towards the negative charges, right? The magnetic force on that electron is pulling it down, but what's going to happen with this electric field? What is that electric field going to start doing to the electrons? It will put a force, an additional force to the electrons, an electric force, not a magnetic one, but an electric one. And the magnitude of that force is equal to the charge multiplied by the electric field. Now, in what direction is the electric force acting on that electron? Since the electric field is down, but the charge is negative, the direction of the force is Q times E. Q is negative, therefore the force goes opposite to the electric field. Right? So the force on that electron, the electric force, it's going to be up. That will be Fe. And we have the magnetic force here pushing the electrons down. So at the beginning, the first electron that starts moving pretty much only feels a magnetic force, right? But as soon as the number of electrons have accumulated at the bottom, there will be an electric field inside this conductor, and there will be an electric force opposing the motion of those electrons. And the more electrons accumulate at the bottom, the stronger the electric field is. So you can imagine that after a short amount of time, there will be an equilibrium between the electric force and the magnetic force acting on the electrons. So when that equilibrium is reached, the electric force will be equal to the magnetic force, the Lorentz force, right? The electric force is in magnitude the charge of the particle times the electric field, and that in magnitude should be equal to the magnetic force, Lorentz force, which is Q V B. And I'm not wondering or worrying about the cross product here, because the direction of V and the direction of B are perpendicular. So the cross product is the sine of the angle is 1. Okay? So, and we know in which directions the forces are going. So this is the condition for equilibrium. When this happens, when this condition is satisfied, there will be no more flow of electrons inside the bar, the moving bar. Okay? So that tells you that the equilibrium electric field is going to be equal to VB, because you can cancel the Q on both sides. So the electric field that is generated by this motion of the bar depends on how strong is the magnetic field, and it depends on how fast this bar is moving. The velocity V, which is the velocity of the bar. Not the velocity, not drift velocity, okay, it's the velocity of the bar. Since there is an electric field inside the bar, you know that there's going to be a difference in potential between the two sides of the bar. There will be the difference in potential, delta V, between the top side of the bar and the top end and the bottom end of that bar. How do I know what's the difference in potential? It's the electric field the integral of the electric field over the path. The electric field points in the direction of the bar. I'm going to move in the same direction from one side of the bar to the other. So the, say the length of the bar, let's say that it's L. So delta V will be E times L. And how much is E? E is V, B, and I multiply that by L. So the difference in potential in this bar, just by moving it in a magnetic field, you would find if you put a voltmeter there, your voltmeter would say that much is the difference in potential between the two sides of the bar. So you have pretty much generated a battery, sort of a battery here, by just taking a bar and moving it through a magnetic field. It's acting as a battery because it's keeping a difference in potential between the two ends of the battery, of the bar in this case.